Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Last couple of classes we have discussed about the shape memory effect, and we have started this shape memory effect discussion with the classification of phase transformation, because shape memory effect is directly linked with phase transformation, and this phase transformation should be diffusionless martensitic transformation, because martensitic transformation is definitely a diffusionless. However, not only martensitic transformation is the only one criteria, rather the reversible transformation is also necessary. Means from austenite the martensite should form by the driving force during cooling. So, thermal cooling provides the driving force for martensitic transformation, and once we get this martensite, then this martensite should contain or accommodate the transformational strain from austenite to martensite by twinning, and then this twin is expected to be two different types. Here type means basically we are talking about twin variant, and these two different variant form during thermal cooling itself. During deformation of this martensite at low temperature, one of these twin grows in expense to other. After that we get actually the strain, means the plastic deformation, means the deformation which creates a permanent deformation, which apparently looks like a permanent deformation, is generated due to the growth of the martensite twin variants, and this strain could be further recovered during heating or increasing the temperature above austenite finish temperature. So, this is a very general theory of the shape memory effect, and now we are more interested to discuss some specific case. A specific case means that we learn that austenite is a phase which transform into martensite through martensitic transformation, and this austenite phase in case of iron carbon system is FCC structure, we call it as gamma austenite. However, this particular austenite phase in case of non-ferrous system may not be all time the FCC crystal structure. Similarly, the martensite phase or martensitic phase not only necessarily has to be a body center tetragonal, which you already know from iron carbon martensite system, right. So, this could be some hexagonal close pack structure or any other face center tetragonal structure or many other crystal structure. So, the way the phase transformation occur will tell us that whether it is martensitic in nature or not, and not like that this is a FCC phase. So, all FCC phase should be austenite. Okay. So, we must clarify those things, and today we must try to understand some of these aspects of our case studies in different alloy system. Now, I already told you that this martensitic transformation in case of a shape memory effect is expected to be thermoelastic in nature. Here thermo means thermal stress that gives the driving force, as well as the elastic, that part also contain another driving force for this transformation. In case of a thermoelastic martensitic transformation, the martensite phase that basically form or nucleate in the austenite, and they grow continuously as the temperature is decreased or lowered. And now, how such thing really happen, I must discuss this with a schematic diagram which is shown in the right hand side. You can see here in this first picture, here we are talking about actually the cooling from a higher temperature, where the parent phase austenite, A stands for austenite here, is stable, and once we cool it down, the austenite will transform into martensite just below the martensite start temperature. The martensite start temperature is represented by Ms, and so we need some amount of driving force, the thermal driving force for that to initiate the transformation, and as we decrease it continuously, the martensite phase will continuously grow. And below, when this temperature reaches to martensite finish temperature, so here all the austenite in the microstructure should be transformed into martensite, and below this MF temperature, all the whole microstructure will contain only martensite. So, here I have austenite plus martensite. So, this is a way, and so here that is why we show that is this is the temperature range where martensite is stable, and this is the temperature range where austenite is stable. However, the driving force required for austenite to martensite phase transformation could be compensated by applying some stress, when stress assists this austenite to martensite phase transformation. Okay. What does it mean? That if we apply stress, then the Ms temperature will be raised. That is what we learned from this Clausius-Clapeyron equation and a diagram. And so, there this Ms temperature can be increased here by the application of stress. In such a situation, we do not call really as a Ms, but rather we call it as Md. It means that the initiation of martensite in a austenite phase, initiation means nucleation and growth by the application of stress that occur at a higher temperature level, and that is why here. And this is the range of stress induced martensitic transformation. So, we can apply both stress and thermal quenching to drive this transformation. And to initiate this shape memory effect or to obtain shape memory effect, in this particular case we can directly start with austenite, and then below MF we get actually the martensite, and then this martensite we basically plastically deform it. Okay. So, that is why this straight bar is deformed or bended. Okay. And then once we raise the temperature, here this is the temperature axis actually. So, this parent phase means austenite start forming, and the austenite will complete the whole transformation, or means all the martensite will be transformed into austenite, and here we will get the original shape as it was. And therefore, here we have martensite, we have strain, and this is actually martensite which is deformed, and here we have austenite plus some martensite, and here we have all austenite which we have started with. And so, the initial shape remain as the same, and this is the shape memory effect. And now, let us again come back what we are talking about a thermoelastic nature of the martensite. So, the martensite plate will form and grow continuously. So, we are talking about in this range, in this temperature range we are talking about where the martensite which has nucleated just below ms temperature, they should continuously grow. So, if I think about a austenite grain and these martensite which form and they form and continuously grow, in this way it should cover the whole microstructure. That is what we are talking about. Now, and it should disappear exactly in the reverse path as temperature is raised. So, that means that we have martensite which has been deformed, however, it should simply disappear by the application of thermal or temperature. So, there should be a balance at all times between two opposing energy term in the system. So, one is the chemical free energy difference, which means delta G C. It is basically the difference between the free energy of the martensite and austenite, that is we are talking about, which drives the transformation. And there is a non chemical opposing energy, that is why we use this term N C. So, this would be there are two of these term, and these two term, one is basically the elastic strain energy, another one is the free energy difference, which is the chemical free energy difference. And this there should be a balance in this whole process, and this delta G N C is essentially the elastic strain energy that develop as the microstructural unit of the new phase here is the martensite, that form in the parent phase as a matrix, and therefore, either cooling or the application of external stress tend to assist the transformation, while heating or unstressing will again reverse the transformation. So, in order to obtain a shape memory effect, this thermoelastic nature of the martensite is very much important. And now, we can always ask, what do we mean by a non thermoelastic martensite? Actually, the basic feature of a thermoelastic martensite is that it forms and grows continuously with decrease of the temperature. But in case of a non thermoelastic martensite, basically there is a growth burst occur. Burst mean all of a sudden the martensite form, and it without showing a very typical nucleation and growth type of features. So, a very burst kind of formation of martensite is a very usual nature or common feature of a non thermoelastic nature of the martensite. But in some shape memory alloy system, it has been observed that non thermoelastic martensite could play also a vital role and which gives some percentage of the shape recovery. So, we like to classify all these different alloys that shows the shape memory effect and let us say pseudo elasticity. So, when we are talking about alloys, it is basically the bulk alloys, like in iron containing alloy, in case of steel also you know that we call it as a ferrous alloy, and there are many non ferrous alloy. In case of shape memory alloys, we also classify very similar way like ferrous or non ferrous alloy. However, these are let us say the bulk alloys, and there are also some other processing technique where people deposit and deposit let us say some of these elements which makes this shape memory effect after alloying, and let us say together nickel and titanium they deposited or co-deposited on a substrate, and such a thin film of few micrometer they are used for making devices. And so, we basically call those thin film as shape memory thin film for devices. those we will discuss later on, but in case of a ferrous alloy and non-ferrous alloy, these are very much important, and so we need to talk a little bit in detail and try to look at what are the common features and how this shape memory effect is developed. However, in general it has been observed that ferrous alloys are very less, because as I told you that twinning is less prone to form in case of ferrous alloys, where a large amount of dislocation are also associated. However, there are always some example where people observe such kind of shape memory effect. So, here I show you a summary of all the ferrous shape memory alloys so far has been discovered and different system. So, very interesting system is the iron platinum system. It is a ordered austenite phase, and people observe such a shape memory effect where the composition range is somewhat like 25% platinum. The nature of this transformation is a thermoelastic in nature. So, here Te stands for thermoelastic martensite, where there are also some example of non-thermoelastic martensite, and in this particular case this phase which is the martensite has a BCC or body center tetragonal structure, and we know that this tetragonality basically develop if very little amount of carbon is somewhat present. So, iron nickel system is also very much well known for showing some shape memory behavior, even though the extent is not very large. And the interesting part here that the MS temperatures are quite a bit low, let us say 131 K or 173 K in Kelvin we are talking about, or let us say below 77 K. So, these are the behavior people have observed at a very low temperature rather, whereas the austenite finish temperature has been observed something like 400 K. And another very important aspect of these ferrous shape memory alloys that they require very particular training. Training means several times you cool and heat the alloy and give some sort of thermal cycle as well as stress in order to get the recovery of the plastic strain. So, that was the very common feature of most of the ferrous shape memory alloys. Now, in case of iron manganese system, this is also another very interesting system where martensite is here called as epsilon, because they have a hexagonal close pack structure. Okay. But in all these cases the austenite is the gamma, which is the FCC phase. So, the shape memory effect is generated which is a property of a phase itself. Even though we talk about alloy and so on, but the plastic strain, accommodation of the strain, all these things appear because of a phase, where austenite is a FCC phase and which transform into BCC or body center tetragonal, or let us say it can be transformed into hexagonal close pack martensite structure. So, here silicon is also important to add, we will discuss later on, even though the silicon is somewhat like 1% or maximum up to 4 to 6% has been observed. In these particular cases, people have observed that these are also non-thermoelastic martensite that form, even though the MS temperature is little bit near the room temperature in all these cases, where this is a typical iron manganese system, where some of the substitution of the other alloying element is also present. The third system, where a martensite has a structure of face center tetragonal, means from FCC austenite it transform into FCT, and here also let us say 30% palladium is involved in this alloy, and here these are thermoelastic in nature, and also the temperature is rather low. However, day by day people have discovered some more, but you see very common nature of all these alloy series, that the phase should of austenite should transform from gamma FCC phase, which is a phase centered cubic structure, into either body centered tetragonal or body centered cubic, or hexagonal close pack, or phase centered tetragonal. Now, we must look at the nature or the morphology of the common ferrous martensite microstructure. So, here I show you some of the common feature that I discussed earlier also, that there are 4 major types of martensite has been observed, even though those are not shape memory alloys. Let us say a conventional martensitic transformation. So, those are a lathe, or let us say butterfly, or lenticular, or plate type of morphology. And here I show you the same 4 major types of martensite phase that form here in case of ferrous martensite, and those are well known. Let us say some of the feature you can see here, these are the lathe type. So, a lathe is a very common feature of the martensite, and here it just looks like a butterfly type of shape. Okay. And now, the plate type of martensite is also common in case of this iron chromium alloy, where martensite forms in these shapes, where a lenticular is also another feature, which is a very common feature in iron nickel system. So, iron nickel system is also well known for such shape memory behavior, and this is a typical lenticular morphology of a iron nickel martensite. Okay. So, it looks like a disc, or some section of a disc actually. Now, very thin plate of alpha dash, which also form in case of a high nickel content alloy with a very low carbon percentage. Usually it has been observed that if you increase some carbon concentration, or otherwise the morphology of the martensite depends on the transformation temperature. Means that if MS temperature goes higher, then from lathe to thin plate type of morphology will change. So, very similarly a plate like morphology or here has been observed in case of epsilon martensite, which has a hexagonal close pack structure that form in a iron manganese system. So, iron manganese is also well known of a shape memory behavior as a ferrous martensite, and here usually people add some amount of silicon. So, epsilon martensite is also very much common to show such kind of plate like features. And all these different morphology of martensite involve this martensitic transformation from austenite and incorporate some defect, so that they can exhibit or recover the strain or the shape strain. A very general statement about the shape memory alloys, one can recall that this iron nickel system with cobalt and titanium addition, or iron manganese system, these are the very two common system or the most important system in a ferrous martensite, in a ferrous shape memory alloys, where the specific thermomechanical treatment must be given, only then the alloy will exhibit the shape memory effect. Here we are talking about heating and cooling and some giving some deformation at a given some temperature, and that is why we are calling it as a thermomechanical treatment, or let us say proper training to the shape memory alloy. So, these alloy exhibit a thermal hysteresis of approximately 150 degrees centigrade, means MS and austenite finish temperature, that hysteresis is somewhat like 150 degrees centigrade. Now, another ferrous alloy with good commercial prospect is basically this iron manganese system, where the silicon is primarily added to improve the shape memory effect, and it rises the critical stress for slip in the austenite. Because as I said that to cause a slip in the martensite, to cause a slip, and it will simply destroy the shape memory behavior. So, we need to add about some other alloying element, so that the twinning can form. And when it is subject to proper training under specific thermomechanical loading path, this shape memory effect or alloys exhibit a complete recovery of the strain. However, the transformational strain is only in the range of 2.5 to 4.5 percentage. So, they are not so high that a large amount of strain can be given in the martensite state, so that you can recover a large amount of strain. So, that is not possible, and that is not the nature of the shape memory alloys in ferrous alloys system. Now, since I said that alloying elements are important in case of this iron manganese system, I am talking about actually iron manganese here. So, this is the manganese content and this is the silicon content, and people have observed that 20% of the strain can be recovered, not a total 20% strain. So, the strain given in the martensite, and out of that strain, or let us say out of 2 or 3% of the total strain, 20% of that strain will be recovered in this composition range, where 90% can be recovered in this. So, there is always some percent left behind. So, it is not a fully recoverable strain can be given. However, if you increase this number of cycle, means the training, or let us say the thermomechanical treatment, then the degree of the shape recovery will improve. So, let us say here iron and manganese system with some amount of silicon, it has been observed that there is some increase of the recovery strain. So, this is also a important information, that in case of a ferrous martensite or ferrous shape memory alloys, a thermomechanical treatment is required in order to obtain a good shape strain. Now, the transformation from a austenite, which is a FCC structure, to a hexagonal close back epsilon martensite, the transformation usually proceed by the motion of a Shockley partial, and every second of the 111 austenite plane. So, this is the 111 austenite plane, and these every second plane here, let us say one of the partial Shockley partial should pass, so that the transformational strain can be accommodated. So, usually this Shockley partial, that 112 type of Shockley partial, there are 3 of such Shockley partial are available here, is shown as a vector, that is B, D and C from FCC to HCP transformation on 111 austenite plane. However, these 3 possible shear direction on these 111 plane, there are 3 different kind of shear system is equivalent that lead to this formation of this HCP phase. However, these austenite to martensite transformation causes a total shear of 0.35. This is a quite large strain actually, and this is much higher than let us say iron carbon system. You know about alpha dash martensite, where there is a transformation strain of only 0.2. So, this is a quite large amount of transformational strains are involved, whereas when we need to get back this recovery of the strain given to the sample, this HCP should transform into FCC austenite. HCP is the martensitic phase. However, one should remember that these partial dislocation where it went in a particular direction, it should come back. So, there should be a reverse movement of these partial dislocation, then only the shape recovery will occur. So, that I summarize in a minute. So, like here the ferrous shape memory alloys, let us say here the reverse transformation occur by the motion of the Shockley partial with 3 kinds of equivalent shear direction from a gamma to epsilon. However, these 3 kind of shear that I show in the earlier slide, actually that plane lead to a FCC crystal with the same orientation. And unfortunately, in case of iron manganese system, these reverse transformation that occur by all these 3 equivalent partial dislocation, whereas if you add silicon into it, then only one type of dislocation they actually involve in this reversible transformation. So, the stress induced epsilon martensite is easily formed by accompanying a slip by the deformation at room temperature, and here we actually add silicon in order to promote the stress induced transformation and increase the slip stress. So, that was basically the purpose, and you can see here the schematically I have shown you a thermally induced epsilon martensite and stress induced epsilon martensite. So, here this is the austenite which is shown as a dotted line, and this is a particular B type of direction where partials has moved, and this is the B actually, and this is the martensite where these are B, C and D, 3 different types of stacking of the thermally induced epsilon martensite. So, today we briefly discussed about the ferrous shape memory alloys, and in the next class we will be starting with some non-ferrous system and we will continue this discussion. Thank you.